Welcome to the DS Incubator. Today it's a special video about how to convert a minimum viable product into production. So this is the idea of taking some code that works for you and converting it into something that works for everyone everywhere. So let's motivate why this is important. So if you wanted to say build a skyscraper, you kind of know that it's something that you cannot just do by yourself. You need to know what to do, how to do it, how long it's going to take, and that's not easy. It's very complex. So even if you wanted to try, civil engineering regulations exist that could stop you from doing it. But software engineer is a little different. It's newer, right? And few people have that intuition because they have been exposed to enough software to know how complex it can be. And there's no regulation that would stop you if you want to do it yourself. So the goal of this article is to help a data science team, everyone from the managers to the software developers, to better understand how software evolves, right? From that early stages where it's still a minimum viable product that works just for a few people in their computers, to something that works for everyone everywhere. In this case, I'm going to be demonstrating the use of R packages to support that process because that's language I'm familiar with. But the process is completely agnostic. It applies to any language. In fact, the idea that is at the core of this presentation is the idea of refactoring, which is a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. So that comes from the book Refactoring, which I totally recommend to anyone who wants to implement changes in a code base. And it's basically a series of very small changes that do not change the behavior of the code. Each change in isolation is not a big deal, but an accumulation of those compound to a potentially very significant restructuring of the code base. And since each step is small, the chances that something will go wrong are low. And another idea is that because the behavior of the code is not changed in any of those steps, the system is kept all the time working, fully functional, also reducing the chances that anything that you break will stay broken. So I'm going to be demonstrating an example in R that comes or is based on an example presented in chapter number 5 of the book R Packages. It's very nicely written. It has it expands on the idea of that in any analysis there might be some R package hidden in it. So that is the R code that you could extract from the analysis because it's something that you could reuse. So beyond the analysis that you're doing with that specific data set, there may be some code that you can reuse and use it in a different analysis, maybe with a different data set or even in a different context. So that chapter of that book focuses specifically on the act of refactoring the R code that is part of the analysis. But here we're going to expand that to include everything that you need to do before you even start restructuring the code, which includes building some infrastructure so that you can support automated testing, for example, and also the act of actually writing the tests to support those refactorings, because refactoring goes completely hand on hand with testing. So the presentation here is split in 4 sequential steps. So first we need to ensure that we can reproduce the analysis script that we want to improve, that we want to convert into something in production. Second, we're going to take snapshots, capturing some key outputs of the intermediate steps of the analysis and the final result. And that will be our kind of first safety net in case we make a mistake. We will have something that tells us, this was a mistake, revert it. And then we're gonna, with that safety in place, we're gonna start actually making some changes to the code without changing the behavior of the code, just changing the structure. And that is to simplify the complexity of the system into smaller pieces that can be understood in isolation and also about which we can have conversations with our colleagues. For example, that could allow us to detect bugs, and then we can discuss those bugs and then eventually fix them in step number 4, which is now that we have tests and now we have code that is very modular, we are now in a good position to start changing the behavior once we know what kinds of behavioral changes we want in the system. All right, so by the way, all these links that you see here are links to, in steps 1 to 4, are links to a live demo of me doing the things that I'm gonna just show. So now my focus is more kind of people of all interests, people with interest in coding, but also people without interest in coding. So for those that are not necessarily interested in writing code themselves, the code that you will just see on screen is probably more than enough. You don't need more details. But if you do need more details because your interest is more in implementing these ideas, then click on those links and you'll see me doing what I'm saying here. Those, by the way, in total sum up to maybe 2.5 hours of video, so it's pretty long. Okay, step number 1 of the process is to ensure that we can reproduce the original code. Typically, an MVP comes, in my case, for example, I'm a software engineer. My typical case is where I get code from someone else that is kind of a draft, it's an idea, it works in their computers, but it's not ready to be kind of shared with the entire world, right? We need to improve it, make it stronger, check that there's no bugs and things like that. So typically, I don't even request Git for that, so people who write that code may not use Git. That Git is a tool that we use to keep track of different versions of the code. So the way they distribute the code is not on GitHub, because GitHub only works if you're using Git. Instead, I typically get it in a folder compressed as a zip file or something, right? So I typically download that from, however I got it, and uncompress it, and it lands in my downloads folder. So in this case, the folder where the code is called MVP, and the file that is this, hosts this computational document is the file written. It's typically written in a file that is a cousin of this one. It's called RMD in R, or another format is called Quarto. And if you are working in Python, it could be equivalent to a Jupyter notebook. So this is what the analysis looks like. So this, let me for one time explain what the analysis is doing. It's extremely small, extremely simple, but yet captures the bigger general ideas that pretty much every single data analysis task or refactoring data analysis task requires. And again, this comes from the book Our Packages, chapter 5. You can go and look at it there. It's very slightly adapted from there. All right, so what this analysis is doing, so basically I'm being asked to improve this code here, is first to attach some packages so that we can use functions that were written by other people in our code. Then here we are reading the data from a directory that is nested inside the same folder where the code exists. So here in this case, in my downloads folder, there is a subfolder called MVP, another one called input, and there is this swim CSV file. Swim CSV is a data set that hosts information about people who went for a swim, and they reported where they went for a swim and what was the temperature of the water. So if we have a look at the data after reading it, the raw data looks like this. There is a column called name, where someone, like for example Adam, then reports where they went for a swim. And Adam said to the beach. And then answered the question, okay, what was the temperature of the water? He said it was 95. Beach is a word used in the US. 95 is a number close to the boiling temperature in Celsius of water. So pretty sure that Adam did not swim in boiling water. And because he's from the US, most likely he reported temperature in Fahrenheit. So 95, we're going to interpret that as being Fahrenheit degrees. But in the same data set, take for example Cora. She went for a beach, for a swim, and she said that she swam at the seashore, she said. She said that the temperature was 28. So those 28 most likely are centigrades, because she said seashore. Seashore is a word used in the UK. So we're gonna do the following cleaning. We're gonna first localize where we think, or what type of English we think these people in the table were using, by just deciding that the words beach and coast are words that people use in the US. And then the words seashore or seaside are words that people use in the UK. So based on what type of English they use, then we can we can convert the temperature to Celsius if it is in Fahrenheit, and if it's already in Celsius, we'll leave it at that. So this is what the first snippet of the analysis is doing. It's converting, first allocating an English type to the where column. So it's if basically it's merging the raw data with this lookup table to look up where these people live, basically. And then once we know where they live, then we can apply this Celsius process, right? So the idea of converting Fahrenheit to Celsius, which is captured in this formula, we can apply it to the English column, but only if the English word is in a US word. Else we are gonna just leave it as temperature. So this is what this snippet is doing. So the clean result could look like this. So the temperature in Celsius reported the temperature in Fahrenheit, like this one, was converted to Celsius. But here we already know that the function f to c here applies x minus 32 times 5 over 9. And 5 over 9 is applied through this function, but also again here. I think that's a bug. And thus, if you Google, how to convert, what was the temperature that Adam reported? 91. So if you want to, 95. So if you want to convert 95 to Celsius, you would get a different result. So this is a bug, right? But you don't jump straight to fixing the bug. In this very disciplined process, you first characterize the bug. Then you have a conversation about the bug with your colleagues, and then you fix it eventually. But first we need tests to make sure that the change even in that place is not causing unintentional changes elsewhere, right? So for now we have to refrain ourselves from implementing the fix. We're gonna just describe it. All right, so finally, with a clean data set, all we do here is just saving that to an output directory that in this case is again inside that the same folder that contains the code. In this case contains the data, the output. And that's a bad thing. So let me make a couple of notes. Not always, but in general, because we are, in this case, we want to write some code that is general and we can share with no limitation, particularly no limitation based on the data being private or public. So if the data is too large, for example, then that already limits the usage of it in our package, because the tool that we use to keep track of the versions of the code, Git, cannot handle very big size files. So the data just could not fit, if it is large, in this case it's small, but if it is large, it could not fit in a Git commit, which is the unit of storage for that tool. And then, as I said before, or suggested before, it might be the case that the data is private while everything else might be public. So if we want to share the code publicly, but the data is private, then we're stuck. We just cannot, right? So the best thing we can do is extract the data outside. So this is the current state of the things with downloads. My downloads folder has this MVP folder that I got from somewhere, and here I have my code, the README RMD, a version of it that shows the outputs, the README MD, which is produced automatically when I render this README RMD, and then we have that input folder, output folder, and then a file that describes that this is specifically not just like any project, but particularly one flavor of a project that's called an RStudio project. That's not important for the purposes of this talk. So, all right, so we would like to start changing things, for example, moving the code outside that directory, because we just said, identify that it contains data and we want to isolate the code from the data. So we're going to build some infrastructure. I'm going to be building an R package. If you want to know more about R packages, you can go to the book here, R packages, second edition. You can use a package called Use This, which has a ton of tools that help you create and manage and build R packages. So the function create package creates an empty package, and then you can start adding things to it. But the beauty of building R packages, or any package in any language, I guess, is that because they are standard, a lot of people build tools around that standard structure. Meaning that, for example, we can automatically run specific checks that verify that the package complies with the rules of what a package should look like. And here this package dev.tools has a function called check. Just by running that, we will know if there's any errors, any warnings, any note. And indeed, if you do that, if you create an empty package and call dev.tools check, you could know that, you would learn that there is one thing you still need to do, which is to decide which license you want to distribute that package with. For example, in this case, I then used another function to use an MIT license. Inside this file, it defines that it's an MIT license. You could choose another one. You could even say that it's a private package. And then here I'm also using another function in the use this package to create a subdirectory called inst exit-data, which is a place where I can put files that will install along with the package whenever someone installs it. So think of a package as just a piece of software. With any piece of software you go, you install the package, you install the software, and of course you expect in your computer something to happen, right? Your system would change, some files will be kind of stored somewhere in your system, you may not where, but somewhere files are stored. And that's what happens. Which files go there depends on a bunch of things. So obviously all these files will go there, and what we put in inst will follow. So will be installed in your system. So we for a technical reason, to fully have access to all the tests and all the checks, we need this file to live here in the inst directory. It's something I'm not going to dive deep now. All right, so once we have that structure, we can actually copy the code into that empty package. So here it is, the code. Notice that there is no more data here. The data is outside. So we're now ready to share this on GitHub. It's super small, there's no data, so we can create git commits, then move that to GitHub and share it with the world. And then the data, even if it was private, the code is public, so it's fine for us to share in this specific case, right? So now what we need to do is we need to kind of tweak, this is a snippet of the file that we're working with. Except that there is something that have already changed. It's this line here. So why? Okay, so if we moved the code outside of the folder where the data lives, the script would break. Why? Because the function here is a function that creates paths that are nested in the folder where the function is being called, the working directory that calls that function. However, we can do a little hack. Instead of starting like crazy rewriting a bunch of lines in the script, every line that uses that here function, we rewrite it to a new address. No, stop that. What you need to do, or a wiser way to do it with a minimal disruption, would be to simply and temporarily do a little hack. We're going to overwrite the here function. We no longer use the here package. If you pay attention at the top, there was another line here that said library here, which is the package here. We no longer need the here package. We are actually going to write our own here function. And instead of using the original definition, we are going to define it differently to point to where we have the data. So I particularly chose to store the data under downloads and MVP. And there, this ... means that I can pass any number of strings here, and that will be used to construct the path. So if I pass swim CSV to the object input name, and then pass input name to the function to the call of here input name, what we are creating here is a path that points to downloads. Maybe you didn't follow that description, but basically with this single line of code, we changed, no matter how many times the function here was used, they will all point now to a new direction. Very minimal disruption, very significant change. All right, and that marks the end of the first and pretty long actually step, which was this idea of being able to reproduce the code from our package in this case, from a tool that has sufficient structures to support the things that we're going to be building in a moment. For example, the tests. So the second step, now that we can reproduce the script from an executable file, now we're going to move to step 2, which is capturing some snapshots of the data as it's transformed inside the analysis script. So I'm going to be creating a new test file. A test file in R, you can create it with the function useTest from the useThis package. So if you give it a name, say capture outputs, it's going to create a new file under the directory tests that has that name. I'm going to show you that in a moment. So the inside of that file is going to be empty, and we can start writing stuff in it. What we write is very meaningful. So in this case, I chose to write 2 tests that would test that the objects localized and clean did not change. So that's my goal, to write some tests that make sure that those objects do not change, because very soon I'm going to be starting to change the code. So I have those tests as safety net, right, for my changes, to make sure that I don't make any mistake. So let me go back very quickly to the script to show you what those objects were. So here it is, localized. So localized will be a safety net for me to refactor this code. All here, I could change now, and as long as the result is the exact same, then that localized object that is capturing my snapshot test would just work. And if I make any mistake, I'm going to get an error message. And then the same thing for this part. So the object clean is going to be my safety net. So if I take a snapshot of it, to be able to refactor everything, here, and even everything on top, because the localized object is a dependency here as well. So if something changes in localized, and the object clean is going to change too. All right, so that's a little bit abstract. So let me show you some things a little bit more concrete. For those who are more interested in less in the code and more in the management of all of this, just learn that we are very in a very structured way starting to create some tests of what our analysis is doing. There is here a little trick. So this function here is the one that I created to be able to access the objects inside the environment where our script runs. So remember, I told you the first step was to be able to execute from a single script the whole analysis. Now we can get inside the environment where that script runs to cherry pick the objects that we want to test. So that object assigns, that script assigns an object called localized. So we're going to access it with this E. Inside this E object, it's an environment, exists this localized object. And I'm accessing that with this function here. So let me show you, I will do the same thing with the clean object. So let me show you a little bit. It's pretty simple, but it's kind of simple what it does, but kind of hard to grasp maybe. So the function armand.render is what allows us to, given a path, in this case the path to the script that we want to refactor, given a path, that function will execute that script. And we are using an argument called envir with the object E. So the object E is something that we create. So we create first a new environment. It's kind of an empty space to store stuff. And then as that MVP is rendered, a lot of objects are being created, and then they're going to appear automatically in that E object. And then we can access them because we're going to output from this function, we're going to output that E environment, and every object that it creates, we can access with $, like clean or localized, right? So that's a hack there. Well, not a hack, that's the trick. With Quiet, what I'm doing is trying to suppress the messages that come from rendering the RMD file, which could be annoying when you test things. All right, so as a result of that, when you run the test with a function called DevTools test, all the tests will run. R will detect that there were some snapshot tests, and it will automatically print the output of the object E-localized and the output of the object E-clean. And this is our record stored somewhere that we have, so that's our safety net. So that if we change something in such a way that the output changes, this test will fail, and we will know exactly in which way. So the new snapshots, when we run them, created this file here. Under a directory called snaps, _snaps, it added automatically this file called capture outputs _.md. And the test that the test file that we created with the function useTest is this one here. It landed in a folder called tests. Then under it, there is a child called test.dat. And under that, we have either the folder snaps and all the files, all the test files. So the prefix test hyphen was added automatically. When I run the useTest function from the useThis package, all I said is, call it capture output. And then the extension R and test hyphen was added automatically. And then this other file is infrastructure, has been added there automatically. So a warning there is the following. If you're going to be sharing this on GitHub, which is great, and if you are going to do it in a public repo, notice that these objects will print and be shared with the world. So if you're using private data, these outputs here are going to be private too. So do not do that, right? So do not create those snapshots. Or even better, you can create them, but you can move your test to a private directory. You don't have to call it specifically private, you can call it whatever. But the trick is separate the tests that will produce private snapshots in their own directory, so that then you can test the whole directory with the function test_dir. So that function will create all the private tests inside a specific directory that you then can add to your git ignore file, so that they are not shared publicly. So you share everything else except that. That has to be generated locally. If you're not one of those tech people in the team, this of course was a lot of technical detail, but you can ignore it. So the summary for everyone here is that now we are entering stage 3. What do we do so far? Well, we first ensure that we can reproduce the script that we are about to refactor, and then step 2 was to add some snapshots to capture some intermediate results and the end result of our analysis, so that we then can start changing code without changing behavior. And that's step 3. That's what we are about to start doing. So here is again our script, now in a form that has been already refactored. Notice that, for example, the name MVP path is a new name. It holds the same function that before was assigned to the here function. So now there's no longer a here function, because actually it's not something that you could leave for a long time. It was just an intermediate refactoring move, so that we could execute the script with minimal interruptions. But now that we have captured some of the intermediate results and the final result, we are already in a good place to start, for example, doing small steps, small refactorings like renaming a variable. That's a pretty safe refactoring to do. Actually, there's automated tools that allow you to detect the same string everywhere and change it automatically, so it's pretty safe. Then a little bigger changes has been to extract all the code that dealt with creating that localization of the beach, and the code that dealt with sensifying the temperature. So that code moved now to the R directory. So let me show you as an example how I did that for, say, sensify temp. So now my script shrunk to this, and the relevant lines, the ones that we extracted in the package, are just these two. All the code now moved to the R folder. I created an R file with the name of the function that I wanted to extract, like this, using the function useR from the useThis package. And automatically, I had a file that was empty, and I started populating that file. The first thing I did is to cut the code from the script, from the MVP script, and I pasted it here exactly as it came from there, including the bug, right? So that's important, that right now we are only focusing on behavioral preserving changes. So even if we know there is a bug, we just leave it alone, and this is just refactoring. And then we also get this little helper function that is used inside this bigger function called sensify temp. Notice that there is nothing on top of F to C. This is what we call an internal function. We don't need to document that function, and we don't need to test it. It's going to be tested indirectly through sensify temp. But because sensify temp is part of the script, it's exposed in the script. It's not used only internally, it's used by our users. Then we have to document it, and this is what the documentation looks like. Basically, it's a bunch of things that you put there that then, when you do question mark and the name of the function that you want to read the documentation for, then you get a very nice HTML version of it, with whatever you wrote there. So you have to be nice to yourself and your users and write meaningful documentation. Particularly really nice examples help a lot. So this function use R. Actually here I made a mistake. This should say use test. That is what would create the test file associated to Sensify temp. And it would again start empty, and here I started writing 3 tests. I'm gonna mention them very briefly to what they do. For example, the first test I chose to write was one that confirms that if the temperature is already in Celsius, it should be left alone. So the Sensify temp, what does takes a table, and this table function creates a table that if the language is UK, the English is in the UK, then we assume that the temperature is in Celsius and it should stay in Celsius. So given such a table, given a temperature in English and the temperature of 32, we expect the output to be also 32, because Celsius would not need to be converted to Celsius. They stay as they are. And so that's the first test. The second test is actually testing that if there is some column missing, so the columns English and the columns temp are used internally by the Sensify temperature function. So if they are missing, we should get an error. So that's what this test is doing. It's making sure that error is somewhat meaningful. And then finally, this is the most important test. Here, I googled, what would be the conversion of 91 Fahrenheit to Celsius, and it was something like 32.8. And so what we get is not that; it's a different result. So it's wrong. This test fails. So if you run that in R, you would get, a very prominent message saying, "Hey, this is wrong." It tells you even, where it is wrong, exactly where to go fix it. But here we are skipping that test, so that we can still we have the proof that the code might have a problem there that we need to discuss, but I'm skipping this test with fix me. This message is going to print every time I run test, which is extremely often, like many times a day, and even many times an hour. And every time I would get a reminder that it's something I need to fix. So what I could do now is leave that behavior as it is, leave the bug there, leave that test there, ready to be modified as soon as the bug is discussed. But first, I need to discuss the bug with my colleagues and make sure that it is really a bug. So that was step 2. So wrapping up, what we did was start making some refactorings, which by definition are changes that preserve the behavior of the code, even if the behavior is wrong. And finally, we reached the point that where we were very excited to get, which is the point where we can actually start improving the software. For example, fixing bugs. So fixing bugs is a behavioral change. So we need to take it, after we have already incorporated some tests. At least one test, the one that proves that the bug exists. So the first step would be first discuss the current behavior. Once we agree it's a bug, go fix it. And then other types of improvements that you could do here is the remove duplication. So that, for example, if there is the same piece of code exists in different places in the code base, you want to make sure that if there is a bug in one place, it's going to be removed forever, right? But if the code is duplicated, then it could be that you remove the bug from one place, but the bug exists still somewhere else. So that's one of the key points of removing duplication. But there is more benefits to it. Basically, it allows the future maintenance of the code. And then once we are at that state with like no bugs, some tests, we are in a position to start developing new behavior. And when we develop new behavior, if we do know exactly what is that new behavior that we want, we can even use a very cool approach called test-driven development, where we first write the test that will pass once the code that implements it exists. But because the code, because you write the test before the code, then that test would fail. And then your next job is to go and make that test pass. When you make that test pass, you already kind of reached your milestone, and then you can start doing refactoring. So that's the idea of test-driven development. There is a whole video actually dedicated to that in my DS Incubator playlist if you want. So here as an example of an improvement, I'm showing that now I'm, here there was some code that was again multiplying by 5/9, and that's gone. So that was the fix, the bug fix. And then the test also, I removed that line that said skip. So now we are not skipping this test. If this test passes, it's because it's correct. So Fahrenheit is converted to something close to 32.8 Celsius, right? And that's the end. And so now the rest of what you have to do is to just enjoy, use that package, reuse it. So here is an example of how it could be reused. So basically the users of that code would simply attach the package with library and the name of the package, in this case production, would use some data, for example in this case is created here on the fly, and then just use the package. So these functions exist in the package. So no longer they need to use, for example, dplyr in this case. They're using Tribble actually, which is also comes from dplyr, but they don't need to. And yeah, so this is the result. So with that, I hope to have demonstrated, the complexity, not to kind of scare you away, just to show the, transparently, what are the techniques that we use, how complex they are, why we do them, and why we need some time to engineer software in such a way that you can build on it like endlessly, right? So if you want to build a skyscraper, you want really strong foundations, and to have strong foundations, starting from an MVP, you need to do these very careful prescripted steps that are very well documented in books, by the way, and hopefully here summarized, so that you make sure that the foundations that on which you want to start extending your software are indeed as strong as you need. All right, with that, I thank you very much.